Thank you. So everybody can hear me well, I hope. So why I'm presenting some research here is that because while I was doing my research, I often saw Corda popping up in the technical documentation and doing the same thing with SGX, and they had always SGX in mind. So what I did is similar to their goals, and so I will present my work. It's a research but practical thing, but I will try comparing it to Corda, what Corda does, so that you can get an idea. So the topic is about private algorithms. I should introduce that. So the main problem is that how do you keep some application logic secret in a remote environment, right? You can obfuscate the code, or you can just try many other things, but you want to have eventually something against reverse engineering, right? So something protected even against side channel attacks and many other things depending on your threat model. I'm supervised by Andrew Martin. My PhD was funded by Intel, but not this work. But also Intel did the same thing, and so you can find the same functionality in Intel SGX SDK now. So you can execute private algorithms with SGX using the same technique I will present. So initially, the SGX application development model says that the enclave code should be public because mutually people will put a trust into the code, they will agree, and they will put data secret. So initially the data will be secret, but not the code. And people should see, and as you could see that here, when you put some algorithm inside, we call it internal enclave function, other than the untrusted part. So this is the trusted part of the enclave. But inside this, you compile it. This is the compiled binary. And until it gets into the memory pages, it is still visible. And this environment is hardware owner's environment. So they can always disassemble the code, right? So this is, that people, enclave code is not secret at the beginning. And you have two ways of protecting, putting some secret code, private algorithm into the enclave. And Corda actually prefers this approach. We do this one, and I'll tell you what are the differences with these two approaches. And this one says that you have an algorithm, private algorithm, you're the business owner, you may not be technical, and what Corda tells you that they will prepare some Java enclave, and it will take your code, dynamically load it on top of the enclave and execute it. But here, they say you just write the enclave. So we call it Enclave-Independent code. You don't need to be an enclave expert, right? Because what Corda says is that C++ development is difficult, so they switch into the Java. But there's the important thing, right? C++ development is difficult because you need to keep things secure. If you do Java, then your Java compiler or JVM would keep things secure. So it is Corda's responsibility now to keep things secure for you. That is difficult, and I'll show you why it's difficult and why we prefer the other approach. Keep using C++, keeping TCB minimized, and etc. So when we look at the enclave-independent private algorithms, you have an Intel SDK or maybe Graphene SDK, some library operating systems to execute the Java, JVM, whatever code. And this increases the TCB size, as trusted computing base size. And what happens is that most people ignore what happens in the execution here, because the JVM initially, or the interpreters, JavaScript interpreter, Python interpreter, these are not designed with security in mind and not with SGX in mind at all, right? So if you put one of the interpreter inside an enclave, this doesn't mean anything is secure, right? You actually even weaken the security guarantees of SGX. And ideally, we want to achieve the small TCB but more functionality. So because if you increase the interpreter, your job is getting difficult, but you need more functionality, so you're in a trade-off. And you need to choose one of them, but you need security as well, right? Practically, just today, you need the security. When you look at the attack surface, you have some browser extension to load the code, and then you have this dynamic code loader, maybe taking the Java code, but then here is we checked the existing, some other research, people put Python code and JavaScript code. So while executing, actually, this becomes the weakest link, and they leak a lot of things. So they claim that they want to keep code secret, but while executing, they leak it, right? And they even weaken the security guarantees of SGX. And here, we assume SGX does the right job. There might be always vulnerabilities, but it can also get patches. So this is not the question here. The problem was over there is that because the interpreter was not designed with security in mind, it has input-dependent control flow here. You can just see what function is mapped into which memory layout, and people can see, like during the execution, you can see, okay, it is calling this function and this function, and you basically get the function names. And it has also a lot of string processing operations with input-dependent data access issues. It's actually not an issue for the interpreter, but it is the issue when you put the interpreter inside the enclave. And what happens here is that it is accessing a table. Let's say if it is the letter C, it's accessing the table 3 times, right? So then you know it is in the C. So you leak the strings as well. But what we propose is that extended enclave partitioning, initially you partition your application to trusted and untrusted parts. And what we do here is that inside the trusted part, we say the public and private internal enclave functions for your trusted part. So the private internal enclave functions will be loaded, fetched later on. And we introduced this early private mode. While compiling the code, you just export the instructions from the memory, runtime memory, into a serialized blob. And so this will be restored later on. So we call it now Enclave-Aware private algorithms, because as an enclave developer now, you need to know what happens with your code. And it will be executed inside the enclave, so you need to understand. So you don't want to get some segmentation fault or problems, right, while you switch between private and public parts of the trusted enclave. So this is going to happen only inside the enclave, and you will never know what happens. And most people say, then, isn't it scary? So we achieved something private. It is in my machine, and I don't even, because initially Intel said code is public, you know what code is running, data is secret. But now we have the code is secret and data is secret, and you don't even know what is happening. So the malware in enclave problem, right? This is an argument. People say, oh, enclave can contain malware. But then look at the business models now, and if it is an issue, you can decide. So when you say computational power as a service, you have an algorithm owner here and a hardware owner, and because you don't have enough computational power, you want to use their power, and you put your application code here into the cloud, and they execute for you. And what happens is that you create the enclave, you measure it, that is your enclave loader here. After verifying it, you send and trigger the secret code, so this is going to be restored, and then you can execute and get your result, and you're done. So here is the so the thread is that as an algorithm owner, you could send the malware to hardware owner, right? But hardware owner is a cloud provider. If you use their resources more, you pay more. And in the beginning, actually, you are free to send any malware as well. So hardware owner, Google or Amazon or whatever company, they don't say that you're limited by not sending malware. You can actually use it for malware too, right? Because it's a server, you rented, you paid, and you can do whatever you want. So this is the same approach, but you don't want them to see your private code. So this is the benefit of SGX here. So SGX can bring malware or not, but it doesn't increase the, it is not a vector for malware to be invisible, or it doesn't get any immediate benefit, because actually enclave is the most visible part in the system. Normally, I have millions ways of hiding a malware in the system, but why should I put my malware into enclave? Because it's visible, actually. All the resources, all the input, output, everything is visible, right? So then the second business model is algorithm querying as a service. You can have an algorithm, and you can actually rent it without disclosing it. And you have the third guy here called data owner, and this data owner controls also the hardware owner's environment. This is the key point. So that this way, the data owner can ensure that the data will not be stolen by the algorithm owner. And the result is returned into the data owner, because data owner wants to query the algorithm, but algorithm owner doesn't want to give it to the data owner or to the hardware owner. And the third thing is that with these 3 stakeholders, algorithm owner, data owner, and hardware owner, we have the data querying as a service. And this is another key point, that we have a filtering, reducing bandwidth operation, because data owner has full control on what data amount will be returned, but not the content. So the data owner doesn't know what is leaked, but it can always control and apply differential privacy filters or privacy budget over the data. Because this guy has an arbitrary computation over the data, health data or DNA, whatever, and this is secret, this should be secret, but then the returned data is only 1 bit, yes or no, if there's a disease or not. So then the data owner has full control on what is learned by the algorithm owner, and it just works as it is. Yeah, cool. So I've just finished it, and we have a paper published in September, so you could read more about how it works. David Gravrock, one of the TPM guy from Intel, he was with us. Andrew Martin, my supervisor. So in the future, we want to put key sharing and separation feature, because now the SGX version 2 is coming, and we will talk about large enclaves, like gigabytes of enclaves. And you don't want to unnecessarily destroy the enclave and create again. You want to make it modular and partial attestation maybe, or partial usages for different people. And you want to separate the keys inside the enclave. And so this modular attestation feature already came out. We didn't integrate it. And you could also even transfer the ownership of enclave by a secure erase, and without actually, again, creating or increasing the cost. And that is all. My talk finished. Now you can ask questions.
Okay. Cool. Can we have this mic on as well? Cool. Okay, we have got one. So I'll start with one on the app, just because it will be a little bit hard, and it's kind of an interesting one. So how much have things changed since you started your PhD, and how has the problem you're trying to solve changed during that time?
Oh, okay. So I started in 2015 with a different problem, which was we called trustworthy remote entity. So it's a mostly privacy preserving operations, and we did that. It is finished, and many other people did that too. And we showed that SGX is a good candidate for it. We considered side channel attacks, and not much, I think, changed since then. So SGX is growing, and we would, or maybe other researchers also expected SGX to maybe like fail with the problems, but Intel has really good strategies. And it is actually interesting because we have 20 other trusted hardware or TEE solutions, trusted execution environments, but Intel made something important, that it passed the sale point. So it's a product out and we can use it. Before that, we also had a lot of processors, and then nobody paid attention. But so it's actually a difficult point they passed through.
Okay, that leads on to the next question. What Intel hardware supported this, and was it built specially?
Say again?
What Intel hardware supported this, and was it built specially? That was the next question.
Okay, like so after Skylake processors, every Intel processor would support i7 and then like all others, if that's the question. So, so what was the second part of the question again? How does?
Was it specially built to support this, or was it an existing?
Well, so I don't know if it is an NDA thing, so I can't say when SGX was placed into the chip, right? So, but we know publicly that Intel was selling SGX much before Intel published SGX in 2015. So we had access to alpha versions, but this is with the public version. So.
Last question on the app, and then I will see if we can take one from the audience, depending where you're standing. Please explain the benefit of early private mode compared to submitting encrypted algorithms later.
Oh, actually, okay, this is maybe misunderstanding. I couldn't explain it properly. So this is not a comparative thing. It is something together. So you compile the code, and while you compile your enclave, you don't want to include the secret parts inside. And then later on, after testing that it is your enclave, which can restore your private code, then you do you release the private part of the enclave, which is some other memory pages basically. So it is something together. So you do early private mode while compiling, and then during execution you restore it. And it's a simple approach. But then we were able to reduce the TCB by 10 comparing to using interpreters, because you don't want to have interpreters, Trust.js or Secure.js. They are also good work, but then they have performance results, but then they don't consider the side channels. So, and then one of the key points is that if you use an interpreter, you need an oblivious interpreter, and this is a difficult job. So Corda would do some maybe anonymization, or I don't know, some compiler level stuff. And they can bring some solution because they probably have money and good engineers, and that's the key point. So from the research world, whenever you have much engineering work, you just stop there, and then you need to continue with others.
Okay, we're actually out of time, so that's prevented me having to climb over the audience to get to people at the back. Kubilay, will you be around today
Yeah,
and
I
tomorrow?
will
So
be
if anyone's
hopefully
got any
tomorrow too.
questions, you can contact him via the app, so don't forget to download it. Hopefully you have by now. Or you can speak to him later over drinks or here tomorrow. Next presentation in here is in 10 minutes from Drumg. It's the last one of the day.